In this video, we're going to look at the direct alkylation of ketones, esters, and nitriles. So if we're starting with any ketone, ester, or nitrile with an alpha hydrogen, if we react that with LDA, we get our enolate, and then we can use that enolate to directly react with an alkyl halide. So the previous ester synthesis reactions that we were looking at, we didn't need to use LDA because we had dual carbonyl with extra acidic hydrogen. Here we don't have that, so we need to use the strong LDA base. I'm going to choose a generic ketone here. If I react that with LDA under non-photic solvent HF, I will form the enolate ion, which we do have the resonance stabilization for. That will then react with our alkyl halide, S and C type reaction, so same restrictions on that R group. And now I have the new carbon-carbon bond formed at that alpha position. If you have a choice of alpha hydrogens, you're going to alkylate at the less hindered position. And the reason for that is this step right here. That enolate has to act as a nucleophile, and the less hindered it is, the better nucleophile it's going to be. So that will be the preference. Let's look at a few examples. Let's first compare this ester using a direct alkylation. Now you have to remember direct alkylation is always going to occur at the alpha position. So this is the bond that I'm going to be forming. So I will have to start with everything else. The alkyl group. So my options are 1 alpha hydrogen in this spot or 2 over here in this spot. If I remove the 1, I will be making a tertiary carbanion. If I remove one of the other 2, I'll make a secondary. So the secondary is less hindered. It will be a better nucleophile. So that's where I'm going to remove a hydrogen and add on my alkyl group. So that means that ethyl group will add over on that right-hand side. So remember that you're looking for the less hindered enolate ion to form, and that is where you will then form the new carbon-carbon bond.